Hello guys, good afternoon and welcome to today's lesson, which is 2.5 Algebra of Functions and Composite Functions. You will see that this topic, Algebra of Functions, or at least this part, is very simple, and this other, the composition of function, is a little more complicated. Okay, so let's start right away. What are the objectives for today? Number one, we're going to define the basic operations of the algebra of functions. Number two, we're going to define the concept of a composite function. And I'm writing here right now the pronunciation, okay? Composite, composite. Number three, we're going to practice some algebra of functions and composition of functions. So let me give you some motivation first in order to enter this topic. So suppose the following. Suppose that you know that some person created two functions, function h and function k. And remember that one of the common conceptualizations of a function is as a machine, okay? So we have two machines or two functions. The first function is h, the second function is k. And what do these machines do? They take as an input the element x and they output the value of the function, okay, h of x. And in here, in k, we have input x and outputs k of x, the value of the function in that specific number or element, okay? So that's what these functions do. They take something in and they produce something out. So far, nothing weird about this. We have talked about this many times. Okay, now suppose the following. You get curious about how these functions or these machines behave internally. Okay, suppose you're a little kid or something and you just try to open everything up, okay, everything that is at your disposal. You try to see what's inside. So suppose that we get curious about these functions and we open both functions, and what we encounter is this. Look at this. First, let's look at the yellow function at h. I'm placing the name in here. So we open the function and we realize that it has another two functions inside. Look, f and g. And let's start to understand or to observe what the function h is doing. So pay attention. X is being inputted to the function h, and the function h makes a copy of x, and one copy of x goes to f, and one copy of x goes to the function g. Now, f and g do their independent processing on x, okay? And they each produce their outputs, right? F produces f of x, and g produces g of x. That in the general case, they don't have to be the same. They are probably different numbers. Now, these two numbers, f of x and g of x, both go into another function, the function plus, which, as you may know, all that this function does is add whatever you input into this function. Okay, it takes two numbers, f of x and g of x, is gonna add them, as you can see here, and that's it. And this value, guys, the value of the sum of f of x plus g of x, is the output, the final output of the function h. Okay, so that's what the function h is doing. It's taking internally what two functions do independently. It's using the outputs of two different functions, and all that h is doing is adding those values independently in order to produce its own output. So that's what the function h is doing. Okay, next, the function k. This is a little more interesting. If you see, k also uses the functionings of a function g or a machine g and a function f or a machine f. So let's try to understand what this function k is doing. K receives an input of x. So here goes the input, and then first this input goes into g. That's the first thing that the function k does. It inputs this value of x into g, and g produces the output g of x. Okay, this is the output of g. Now, g of x is taking now as an input for f. We're gonna put this value g of x into f, and f obviously is gonna do its processing on g of x, and it's gonna produce its own output, which is f of g of x. I know this sounds complicated or looks complicated, but it's not. It's the same idea we have been using. Okay, this thing is simply the output of f once you give it the corresponding input, which is g of x. Okay, and that's it. So now this value f of g of x is being outputted by the function k. Okay, it's the final output of k. So again, let me rephrase that. K, what k is doing is this: it's taking two functions that are already made, so to speak, and all that k does is put them in succession and apply a process to k first by g, and you have this output, and now this output goes into f, and now you have this output, and this is the final output of k. Okay, so this is basically like a factory works. Okay, in a factory, what you have is a succession of machines working in one after the other. Okay, so that's what is happening right here. Okay, this is called a composition of functions, and we're going to understand that in a moment, more in depth. Okay, so let's first go into the algebra of functions. Let's read. The algebra of functions is very similar to the algebra of real numbers, save for a small difference. I'm going to tell you about this small difference in a moment. The algebra of functions allow us to create new functions given some initial functions. So let's start to read. Given the functions f and g, we can create a new function, h, by doing algebra on f and g in a very similar way in which we do algebra to numbers. Okay, so for example, if I add f of x plus g of x, I can create the function addition, okay, of f and g, which in this case I'm calling h, or sometimes it's called f plus g of x. Okay, as you can see, these two statements on the same number, they are actually the same. Okay, I'm adding the values of the function f and the function g, and I'm producing a new function which is called this f plus g of x, and it's simply the addition of f of x and g of x. And the same for the rest of the operations. We can create, if I'm given f and g, and if I subtract their values, like in this case, I'm creating a new function. And this new function first calculates f of x, then calculates g of x, and then subtracts those values. And it's also written sometimes in this way. Okay, f minus g of x equals f of x minus g of x. And the same for the rest of the operations. I mean multiplication and division. Okay, look at this. We are creating a new function, h of x, which is equal to the multiplication of f of x times g of x. And this is also known commonly as f times g of x. But it's the same. Can you see? It's actually the same. And the same for division. Now, a very important remark is the following. In each case, in each of these four cases, the new function h is defined only in the common domain of both f and g. And this is that small difference that I talked about. Okay, we're going to understand this in a moment. And as I always tell you, it's simpler to get to know these things by doing them than by looking at all of this symbology and all of these definitions. So let's start practicing algebra of functions. You will see that it's actually very simple. So example number one. We are given the functions f of x equals 2x and g of x equals x squared. And we are asked to calculate f plus g, f minus g, f times g, and f over g. Okay, so let's start. So let's first calculate this new function, the function that will be the addition of f plus g. So it goes like this. F plus g of x is nothing but f of x plus g of x. That is by definition. Okay? So we continue. This is equal to f of x plus g of x. But what is f of x? F of x is 2x. So I just put it in here. Plus g of x, which is x squared. And that's it, guys. We are done. Can you see how simple it is? There is nothing else to be done. We already added f of x plus g of x, and this is what we get. So this is a new function, which is known as f plus g of x. I'm going to repeat that. F plus g of x equals 2x plus x squared. That's it. Now, sometimes if you want, I think, and I do this very often. First, what I do is this. I introduce my reader to the following notation. I'm going to say this. Let, well, I always write in capitals, so let h be the following. Okay, I'm going to represent f plus g with this letter h. Let h be h equals f plus g. And with this in mind, now all I can do is this. H of x will be equal to f of x plus g of x. And it's going to be the same as before. 2x plus x squared. So h of x, which is the addition of f plus g, is equal to 2x plus x squared. I like this better. I like this better. Instead of writing this, which is exactly the equivalent thing, okay? This is what I'm writing right now is exactly the same. But the problem with this type of notation is that this sounds weird. Look at the way it sounds. F plus g of x equals to x plus x squared. That is, I don't know, I just don't like it. And from my experience, most mathematicians do not like this type either. We prefer to first give this definition. We say, hey, look, h is equal to f plus g. And with that in mind, with this uh, prologue, so to speak, we can do this. Okay, so these two things are equivalent. Okay, so this is done. Now f minus g, okay, let's write f minus g of x is equal to f of x minus g of x. And so f minus g of x will be equal to 2x minus x squared, and we are done. Or also, we can make the same thing that I told you a moment ago. You specify that h is equal to f minus g, and with this in mind, I can write this. H of x equals 2x squared. So this thing and this thing are equivalent. Now let's go to f times g. Okay, f times g of x is nothing but f of x, and so therefore f times g of x is equal to f of x, which is 2x, times g of x, which is x squared. Now, if you leave it like this, that's already perfect, okay? You have completed the task. But sometimes we actually like to simplify a little more, right? You can actually perform this operation. This will be 2x to the cube. And this is the most common way in which you will encounter this exact exercise. This would be the solution, so to speak, the written solution. Even though it's the same as this, most mathematicians would actually simplify it into this notation. Okay, so that is f times g. And finally, f over g. F over g of x, or also written in this way, f over g of x is x over g of x. So let's do it. F over g of x is equal to f of x, which is 2x, over g of x, which is x squared. And again, this is already completed. This is already a good answer. But we like to simplify this. We can simplify this in this way. And by now, again, you should know why this is the same as this very quickly and very naturally. So this is the solution. Okay, so as you can see, the algebra functions is carried out in the same way that we do algebra with numbers, save for a small difference, which I'm gonna talk in the next examples. Okay, just have that in mind. Example number 2. Given f of x equals x to the cube and g of x equals x to the cube minus x to the square, calculate f plus g, g plus f, f minus g, g minus f times g, g times f over g, and g over f. Okay, because obviously they may be different, right? It may be different adding f plus g than doing g plus f, or f minus g and g minus f. They may be different. Okay, so let's see how this works. I'm gonna do it very quickly. So let's go first with f plus g of x. I'm gonna do it directly now. F of x is equal to x to the cube plus g of x, which is all of this, right? Let me put this into parentheses. So this is f of x plus g of x. And if we simplify a little, we get 2x to the cube minus x squared. So this is the solution to this first exercise. F plus g is equal to this. Okay, done. Now let's calculate g plus f. G plus f of x. That's going to be g, which is equal to x to the cube minus x squared, plus f, which is x to the cube. So if I simplify this, I'm going to get, again, the same answer. Okay, as you can see. So for addition, f plus g and g plus f are actually the same function. There is no problem in here. And we say that the operation of addition is commutative. I had already told you that word, commutative. Okay, this operation plus is commutative with respect to functions. And that means that whether you do first one function plus the other, or the other function plus the first one, it doesn't make any difference. Okay, the other doesn't make any difference. That's what this word means, commutative. Okay, now let's go into subtraction. F minus g first, and then g minus f, and let's see whether the same happens, whether it's commutative or not. So let's first do this, f minus g. So f minus g of x is equal to f minus g, and let's simplify a little. Okay, we have x to the cube minus all of this. Try to do it in the mind quickly, it's very simple. You should get this, right? The final simplification of all of this is x squared. Okay, now g minus f, let's calculate it. First g, which is this, x to the cube minus x to the square, minus f, which is x to the cube. Okay, do this mentally, the simplification of all of this, and you're gonna get minus x to the square, right? So as we can see now, f minus g of x and g minus f of x are in fact different. You know, a single symbol, a single sign is enough to say that these two are different. Okay, they are different. And in fact, in the general case, this doing this and doing this is different. Okay, so we say that subtraction is not commutative. It's not commutative. It's not the same subtracting f minus g than doing g minus f. Okay. Same with this two, f times g and g times f. So very quickly, f times g is equal to x to the cube times x to the cube minus x squared. And let's simplify this. We get x to the 6 minus x to the 5. Perfect. Now let's do g times f of x. That's going to be x to the cube minus x to the square times x to the cube. And actually, we're going to get the same. Okay? As you can see. So multiplication is also commutative. And finally, f over g and g over f. So let's write f over g of x is equal to f over g. Okay, and we cannot simplify this. Uh, we cannot do it. And g over f of x will be g, which is this, over f, which is this. And as you can see, these two things are different. This fraction and this fraction are different. Why? Because, I mean, it's clear, right? The numerator and the denominator are in different places. It's not the same having 1 over 2 than 2 over 1, or 4 over 7 than 7 over 4. So these two things are different. And so again, one more time, we say that we say that the division of functions is not commutative. These two things, in the general case, they are different. For some specific case, they may be equal, but in the general case, they are different. And these two things are always equal, as the same as this. This and this is always equal, no matter what. Okay, example number 3. Given f of x equals x plus 1 and g of x equals 1 over x, calculate f plus g, f minus g, f times g, and f over g, and evaluate these new functions, each of these functions, in two values, x equals 2 and x equals 0. So let's do it quickly. F plus g of x, how much is that going to be? Well, that's going to be f, which is x, plus, no, sorry, x plus 1, this is f, plus g, which is this. Okay, this is f plus g. Now let's evaluate in 2 and in 0, in these two values, very quickly. So f plus g evaluated in 2 is going to be 2 plus 1 over 2, and that's going to be 3 plus 1 half, that's going to be 7 halves. Okay, so everything perfect. Now f plus g evaluated in 0 is going to be 0 plus 1 over 0. And look at this. What is happening right here, right there? A division over 0, right? Which is not allowed in mathematics. So what do we say? We say the following. We say that f plus g cannot be evaluated in 0. 0 is not part of the domain of f plus g. And if we look at each of the functions independently, first look at this. What is the domain of this function? The domain is all the real numbers, right? Because nothing, you can give f any real number and it's not gonna crash. Nothing weird is gonna happen. No divisions over 0, or no even roots of negative numbers. So the domain of this is all the real numbers. The problem comes with this function. This function's domain is all the real numbers except the number 0. You cannot give this function the number 0. So when you add both functions and you produce this new function, what's going to be the domain of this new function? Does it have something to do with the independent domains of each of these functions? Yes, it has to do. And the domain of this new function is it's said to be the intersection of these two domains. Okay, so it's gotta be like it has to respect each of these two domains. So f plus g has to respect both domains, and that's why since the domain of G doesn't include 0, okay, then the domain of f plus g has to exclude also 0. So the domain of f plus g is all the real numbers again, but excluding the number 0. And that is the small difference I told you at the beginning. Okay, you cannot just add like two functions like that and evaluate them in any value you want. You have to respect the initial domains of each of the initial functions. I don't think I have a lot of time, so I'm gonna skip these three, okay? But you get the idea, I believe. Example 4. Given f of x equals the square root of x and g of x equals x, calculate one more time four functions: f plus g, f minus g, f times g, and f over g. Okay, and then we're gonna evaluate these new functions in x equals 9 and x equals minus 9. I'm only gonna do this and this. Okay, so I'm just gonna do these two. So let's do it. F plus g, f plus g of x. That's gonna be equal to f of x, which is this, the square root of x, plus g of x, which is x. So this is the function, okay? The square root of x plus x. This is f plus g. Now let's evaluate in x equals 9 first. So f plus g evaluated in 9 is going to be the square root of 9 plus 9, which is 3 plus 9, which is 12. So far, perfect. Now, what's going to happen if I evaluate in minus 9? Let's see. F plus g evaluated in minus 9 is going to be the square root of minus 9 plus 9, and that's where we have a crash. Okay, because remember, we cannot evaluate even roots of negative numbers. So again, what is the solution to this? None. This evaluation cannot be performed. The function f plus g is not defined in this number, in minus 9. And in fact, it's not going to be possible to evaluate this function f plus g in any negative number. Why? Let's go back here. Let's analyze the initial functions. This and this. I'm going to start with this one. What is the domain of G? The domain of G is all the real numbers, right? Because nothing weird is going to happen if I give G any real number. And what is the domain of F? F is the square root of X. So when I calculate the domain of F, as you may know by now, this is only going to be all the numbers X such that X is greater or equal than 0. Why? Because this function doesn't accept negative numbers. The domain of this function is basically 0 and all the positive numbers. So this new function f plus g, which is created using f and g independently and then summing them, has to respect both domains. Okay, and what is the most restrictive domain? This one, right? This domain has no restrictions, but this one does. So whatever restrictions this domain implies on f, those restrictions are going to be inherited to f plus g. That is the word, inherited. These restrictions are going to be inherited to f plus g. So if this domain, the domain of f, doesn't allow negative numbers, then so the domain of f plus g. No negative number is going to be allowed in this part. No negative number at all. So that's how it works. That is the only small difference between doing normal algebra and doing algebra of functions. That you have to respect the domains of the initial functions. Perfect. Now let's go. That was algebra of functions, guys. Okay, that was algebra of functions. Like you realized, or like you must have noticed, it's very simple, and that's it. Okay, there's not much to talk about that. Now, composition of functions. This one is actually a little complicated to understand, and it's much more interesting. This operation, because it's actually an operation on functions, allows you to create very powerful new functions and to make a very good analysis of functions. So let's read. Given two functions, f and g, we can create a new function called f composed with g, or f circle g, or f of g. And there are actually many more, okay, but I'm gonna stick to these three. And it's represented by f, a little ball or circle, and then g. Okay, so again, how do you read this? You read this in the following way: f composed with g, or f circle g, or f of g. And there are many more. There are like 7 or 8 ways to pronounce this symbol, okay? But these are the most important ones. En español esto se dice F bola G, así se dice, F bola G, o F compuesta con G. Okay, so what is this new function? How does it work? This new function is defined as the following: F circle G of X is equal to F evaluated in G of X. F evaluated in G of X, or I'm going to pronounce this in another way: F of G of X. Okay, it looks like, it sounds like a, what do you call these things, tongue twister or something. It's very complex to pronounce this: F of G of X. Well, it's not really complex, but it's weird. It's just weird. Okay, now a very important remark is also this one, and this is similar to the one about algebra functions. This composite function, f composed with g of x, is defined for all x such that g of x exists and also f of g of x exists. Okay, I'm gonna try to explain this clearly in a moment with the exercises. So let's go to the exercises. We're gonna go through 3 examples. So this, given f of x equals x plus 2 and g of x equals x squared, calculate f composed with g and g composed with f, or f circle g and g circle f, or f of g and g of f. So let's do this. So let's first do f circle g. F circle g of x is a function that is created by evaluating f. I'm going to evaluate f in what number? In g of x. Okay, so that this is the definition, guys. Just stick to the definition and work with it. Okay, so this is equal f circle g of x is equal to f evaluated in g of x. But what is g of x? G of x is this, x squared. So I'm going to put that number in there. You see, g of x is equal to this. So whenever I read g of x, I'm going to put what it is in there. So f of g of x is equal to f evaluated in x squared. And then we continue working. So now f circle g of x is equal to f evaluated in x squared. But what is f? X is this. F of x is this. So I'm going to evaluate the function f in this value. If f of x is equal to x plus 2, then f of x squared is nothing but x squared plus 2. Can you see what I did? Look at the function. F of x takes the number x and it outputs the number x plus 2. So clearly f of x squared is going to be x squared plus 2. Try to understand this. It's the same that when we do this. I mean, if I evaluate f in 3, that's going to be simply 3 plus 2. I'm just substituting this value whenever I see the x, right? And if I'm given this value to evaluate, then I do exactly the same. I just put it whenever I encounter the x. Let me erase all of this. Okay, so f circle g of x is simply x squared plus 2. We are done. We have calculated f circle g, or the composition of f and g. This is the composition of f and g in that order. Now, let's do now the composition of g and f. The order is different. First appears the g, and then the f appears. So let's do this one. G circle f of x is going to be equal to g evaluated in f of x. So let's continue working. G of f, or g circle f of x, is g evaluated in f of x. But what is f of x? F of x is equal to x plus 2. So I'm going to put that value in here. Let's continue working. G of f, or g circle f of x, is equal to g evaluated in x plus 2. But what is g? G is the function that takes a value. G is the function that takes the value x as an input, and it outputs the square of such value. So g evaluated in x plus 2 is going to be the square of all of this. So it's going to be equal to x plus 2 to the square. Can you see? And we are done. G of f of x is equal to x plus 2 to the square. Okay, and we are done with this example. We have calculated f of g, and we have calculated g of f, or f circle g and g circle f. Okay, and look at the results, guys. Look at the final results of each one. In this one, the result is x squared plus 2, and in this one is the square of x plus 2. Completely different things. This and this are completely different. In here, the square is only applied to the x, and then we add 2. And in here, we first add 2 to x, and the result is being squared. So as you can see, one more time, that word commutative. Okay, that word commutative. We say that f circle g is not the same as g circle f, and therefore the operation of composition, which is represented by this circle, is not commutative. Is not commutative. In order for something to be commutative, they have to be, the order should have no importance. So in this case, since the order matters, then this operation, the operation composition, is not commutative. Next example. Given f of x equals x squared and g of x equals 1 over x, one more time, calculate f circle g and g circle f. And now evaluate these new functions, f circle g and g circle f, in two values, x equals 2 and x equals 0. So let's do it. First, f circle g of x. That's, by definition, what that means is f evaluated in g of x. That is the definition. And I work with my definition like a machine, you know. I just stick to my definition like a robot. So first I write f, and I'm going to evaluate it in g of x. What is g of x? G of x is equal to 1 over x. So I'm going to put it right there. Continue working. F of g of x is equal to f evaluated in 1 over x. But what is f? F of x equals x squared. So whenever I see the x, I'm going to substitute it for 1 over x. If f of x is equal to x to the square, then f of 1 over x is going to be 1 over x to the square. I'm just evaluating the function, guys, in this value. And that's all that's happening, you see? I'm done. f of g, f of g of x is equal to 1 over x, all of that to the square. Perfect. Done. Now let's calculate first. Before we evaluate these functions in these two values, let's calculate g of f. So g of f, I'm just gonna do it, okay? And try to follow me by just looking at the symbols, because I get tired with my voice. Sorry about that, but it's true. I hope you have understood that part, okay? G of x is simply 1 over x. G evaluated in x is simply the same as 1 over x. So g evaluated in x squared is simply 1 over x squared. Okay? And we are done. That's it, guys. We are done. Okay? So one more time. One more time. Uh, are these functions the same? In this case, they are the same. Okay? For the simple fact that when you elevate one to any exponent, you actually get 1. But if this was any other number, let's say in a 2 or a 3, if this was any other number except 1, these two functions would be different. So this is a case in which f of g and g of f is actually the same for any number x. So it's a coincidence, okay? It's just a coincidence. Okay, so now let's evaluate these functions in x equals 2 and x equals 4. I'm going to first evaluate this function in 2. I'm going to do it in blue, and I'm going to do it over here, okay? So let's evaluate f of g in the number 2. So that's going to be equal to 1 over 2 to the square, and that's equal to 1/4. So perfect, no problem, everything fine. Now let's evaluate this same function in 0. F of g of 0 is equal to 1 over 0 to the square, and we have a crash. Okay, we cannot divide over 0, therefore we say the following: this function f of g of x made with this function and this function initially also has to respect the domains of these two functions. Okay, I cannot evaluate this function f of g in 0, and the reason is that this function g is not capable of being evaluated in 0. Okay, so 0 is not part of the domain of f of g. Okay, and since g of f is actually the same function as this, I'm gonna get the same values, right? For these two evaluations, for 2 and 0, I'm gonna get 1/4, and I'm gonna get a crash. So we're done with the example. One more. Given f of x equals the square root of x and g of x equals minus x squared, calculate f of g and g of f and evaluate these new functions in x equals 1 and x equals minus 3. So very quickly, f of g of x is by definition f evaluated in g of x. So we continue working. I'm gonna work as fast as I can. F evaluated in g of x, which is minus x squared, like that, and then f of g of x equals f evaluated in minus x squared. So that's going to be, since f is equal to the square root of x, this is going to be equal to the square root of minus x squared. So this is f of g of x. or f composed of g, I'm sorry, f composed with g of x, or f circle g of x is equal to this. Now let's calculate g composed with f. G composed with f of x is by definition g evaluated in f of x. So I keep on working. What is f of x? F of x is the square root of x. So I put it there. Let's continue. G of f of x is equal to g evaluated in the square root of x. So when I evaluate g in x, it gives me the negative of x to the square. Then when I evaluate g in this value, it's going to give me the negative of such value to the square, like so. And I can simplify this a little more, right? Because, let me write this. Because this is the negative of the square root of a number to the square. But remember, the square is only being applied to this value, to the root, not to the sign. So this is going to be the same as minus the square of a square root, which is the number itself, right? The radicand. So this is minus x. So we're done. G circle f of x is equal to minus x. Okay, now let's analyze these two functions, guys. Like I said before, they're not the same, which confirms the fact that f of g and g of f are different in the general case. Okay, the composition of functions is not commutative. And let's try to evaluate these functions in 1 and in minus 3. And let's see what happens. I'm going to do that in blue again over here. So f of g evaluated in 1. Let's see what happens. That's going to be the square root of the negative of 1 to the square. Okay? And what's going to be that? The square root of the negative of 1. We have a crash. We cannot evaluate this function in 1 because of this, right? Now let's try to evaluate in minus 3. F of g of minus 3 is equal to the square root of the negative of minus 3 to the square, which is equal to the square root of the negative of minus 3 to the square. How much is this? It's 9. And again, we have a crash. And if you notice, it doesn't matter what value we evaluate this function in. It doesn't matter what x I put in here and in here. I'm always going to have this problem because if you look at this, we have the square root of the negative of this number. The square root of the negative of this number. But this number that I'm circling right now, for any x, this number will always be positive. Always, no matter what x, because it's being raised to the square. So we will always have the square root of the negative of a positive number. So all of this in the end will be a negative number, no matter what the x is. So this function, and please listen carefully, this function f of g cannot be evaluated in any number. Basically, this function doesn't exist. I cannot compose f circle g. This function does not exist because it's not being able. It's not capable of being evaluated in any number. So what do I want this function for? It doesn't even exist. Okay, so that's very important for you to notice. You have to check your final functions in the end, whether they make sense or not. So f of g cannot be evaluated in any number, and therefore it doesn't even exist. Okay, it's of no use at all. I cannot do this. Now on the other hand, g of f of x is simply minus x, and this function is a very decent function. It can be evaluated anywhere. Doesn't matter what value I put here. Okay, this function will always have an output, a decent normal output. Okay, so try to look at the difference. This function doesn't even exist. It doesn't make mathematical sense to compose f and g, but g composed with f is a very decent function and perfectly normal. Okay, so be aware of that. Okay, long class. So we're almost done, guys. So that's the composition of functions, guys. It's basically evaluating a function on the output of another function. And I'm gonna with the next interpretation, I think you're gonna get it. You're gonna get the concept perfectly well, because one thing is doing it like this in these examples, and another thing is actually understanding what's happening. Okay, so look at this. I'm gonna give you an interpretation of a composite function. Composite function. Okay, look at this. Uh, please have your eyes where my cursor is, and don't look at anything yet at the rest. So let's suppose we create a function s, that takes as an input some guy with a beard, and it shaves this guy. Okay, so it's going to produce as an output a cleanly, freshly shaven guy. Okay, so that's what this function is. Function s, function shaving. Perfect. This is simple to understand. Now, what if I told you that this function s, shaving, can be implemented or can be think of by making use of two simpler functions? Okay, look at this line now. I'm creating two simpler functions, function f and function r. What is function f? Function f takes as an input a guy with a beard. Okay, so it goes in, and as output it produces a guy with foam, with shaving foam on his face. Okay, that's what this function is. Function f is function foam. It takes some guy in with a beard and it applies foam to his beard. So this is the output. So if this is x, the input of f, x goes in and f outputs f of x. Can you see? Which is a guy with foam in his beard. Okay, now what can we do with this guy now? We can take this and input it in R, another function. What is R? R stands for razor. So now this function takes this guy, takes it in, it shaves or it razors. Okay, it razors all the beard, all the hairs, and now it outputs a cleanly shaven guy. Okay, so this is represented in this way. The function r takes as input this value f of x. This is the input for r, and r is gonna output obviously r evaluated in f of x, which is nothing but r composed with f, or r circle g. I'm sorry, r circle f. You see, this is a composition of functions, guys. What I'm trying to explain to you is that a composition of functions is creating a new function. Okay, s, this is s, right? All of this is s. S is the composition of f and r. Okay, no, sorry, the other way around. S is the composition of r and f. It has to be said in that precise order. S is the composition of r composed with f, and what that means is that s uh, puts these two functions to work one after the other. First, the one that is the rightmost, this one. So first, how do you shave? You first apply foam on your face. And once you have done that, you do the razoring. Okay, so that's s, guys. S is a composite function. It's r composed with f. F takes place first, and then secondly r. And by doing these two things, you are creating a function which may be called shaving. Do you understand what is happening? It's basically applying functions one after the other. That is the composition of functions. Applying functions one after another. And the first function that is applied is the one that appears the rightmost in here. First f and then r. Okay, now a bad idea would be the opposite case, right? Imagine that I try to implement this function s as f circle r. Okay, f circle r. So that function, what it would do is this. First, it implements R. So it takes a guy and then takes it to the function R. And remember what this function does. It raises the guy. So now you're going to have a razor guy with some dry skin, right? Because you have to apply foam in order for this to work correctly. So this guy is going to be a little unhappy about it. And then this guy is taking as an input to foam, okay? And foam takes us gives us an output a shaven guy. I mean, this guy is already shaven, but now the final product is that this guy is going to have foam on his face, which is completely not ideal, right? I mean, you don't want to end this process by having foam on your face and going out with your girlfriend or something. Okay, so this is incorrect, and this is so that you understand that this function f circle r is not the same as r circle f. So the moral, r of f of x is not the same as f of r of x, or the same thing said in a better way. R composed with F is not the same as F composed with R, because in this composite function, what takes place first is F and then R. And in this function, what takes place first is R, the razoring, and finally the foam, which is not what you want in this case, right? These two things are mostly, in most cases, different, and you have to understand that. And you have to understand what a composite function is. It's simply a function that has two other functions inside, okay? That's basically what's happening. And it puts to work first one function, and the output of this function is given to the other function. Okay, and so on. That's how this works, guys. You have to understand the concept. And one final example of interpretation. When we make tortillas, okay, I assume you have seen this machine in las tortillerías. So this is a complex machine, right? And basically what this machine does is it takes some input in here at this point, which is some mass. Okay, the people put some mass in here, and as an output, okay, after all the process is done, you're gonna end up with some tortilla in here. This is the final output. So I'm gonna call this function all of this machine, all of it, I'm gonna call it T for tortilla. Okay, so T, what it does for you is this. You're gonna give T some mass, this is the input, and T is gonna produce its result, T of M, and all of these will be a tortilla. Okay, you give this input to T, and T will give you this output, and all of these will be a recently cooked tortilla. Fine, that is simple to understand. Now you have to understand this machine or this function has many internal simpler machines. Okay, this is composed of many internal simple machines. Let's go into three of them quickly. As we can imagine, even though we may not have seen this in functioning, what this machine does is this. First, you input the mass in here, and then some part over here produces a ball of mass. With the mass that you put in here, a very shapeless mass, the first machine that is over here, let's suppose, this machine produces a ball with that mass. Okay, so I'm gonna call this machine B for ball. What this machine does is takes mass, shapeless mass, and it's gonna shape it into a ball. That's what this machine does. So we have already one machine, and that's the first machine that is put to work, right? The machine ball or the function ball. Okay, now there must be another function, another machine over here, that what it does is it takes this ball as an input, and then it's gonna press it into a flat disc, right, into the shape of a tortilla. That's what this machine does. It's its only function, taking a ball of mass and producing a flat tortilla. Okay, that's what this function is. So it's another function. We have another function, function P, function press, function B, ball, function P, press, because it's gonna press the ball into a flat disk. Okay, and now we have the final simple machine. There is another machine over here, which is machine C for cook or for cooking, which takes as an input, takes a flat tortilla which is not cooked, and it's gonna cook it. Okay, because over here we have the uh, what do you call an horno? I forget a lot of things. Okay, we have an horno here. Okay, a furnace, sorry, and that's it. The furnace is gonna cook the tortilla, is gonna output it over here. Now we have a cooked tortilla, and then this thing goes and it falls down, and this is the final product. Okay, so all of this machine, which can be conceived as machine T, the machine that produces tortillas, is actually composed of many simpler machines: machine B, machine P, and machine C. Machine ball, a machine that makes balls; a machine P, which takes a ball and presses it; and then a machine C, which takes a pressed ball and cooks it. Okay, that's it, guys. This function T is composed of the function B, the function P, and the function C. And the correct implementation of the whole process is in this way. It's gonna sound weird, but I try to understand. The function T, evaluated in a piece of mass, is simply the function C evaluated in the function P evaluated in the function B of M. Okay, this is the whole process. This is a triple composition. Okay, this can be written in this way: C composed with P composed with B, or C circle P circle B, or C of P of B. It's gonna take you some time to get used to the terminology and the sounds. Don't worry. What does this mean? What does this and this mean? What it means is this. First, we put to work the machine or the function B. Okay, we give it a piece of mass to the machine B, and the machine B will produce a ball. And all of this thing that I'm circling, that's the ball. That is the final product of the machine B. Now, this ball, you're gonna give it to P. Now, you're gonna evaluate P in that ball of mass, and what P is gonna produce is a pressed ball of mass, the flat disk, which I'm circling right now. All of this is now the flat disk of the tortilla. Now, you're gonna give C that flat disk of a tortilla, and the function C will cook it, and that's it. First we implement B, first we make the ball, then we press it, and then we cook it. And that's what the machine T is doing internally. It's composed of many simple machines working one after the other to produce a final product. Okay, that's the interpretation of all of these, guys. That's the interpretation of a composite function. I hope you have gotten it. uh, you're gonna get used to the way we pronounce this. I know it's very weird, and it's like a tongue twister, but I mean, it's a new language, like I've been telling you, and you're gonna get used to it with time. So that's it. This was a very long class. I think I'm gonna have to part it in two videos, and that's it, guys. Now let's go into the activities.